Slightly soluble salts is the name of the PowerPoint video for today. Oil paints contain pigments that are very slightly soluble in water. In addition to chrome yellow, examples include Prussian blue, the reddish-orange color vermilion, and the green color viridian. Solubility equilibria. All ionic compounds dissolve in water to some degree. However, many compounds have such low solubility in water that we classify them as insoluble. We can apply the concepts of equilibrium and use the equilibrium constant to find the concentration of the insoluble salt in water. Solubility is the amount of solute that will dissolve in a given amount of solution at a particular temperature, usually measured in grams per 100 milliliters. Molar solubility is the number of moles of solute that will dissolve in a liter of solution. Converting from grams per 100 milliliters to moles per liter involves changing grams to moles and 100 milliliters to liters. As an example, we're given the solubility of barium selenate as 0.0118 grams per 100 milliliters of solution. What is its molar solubility? So we're going to have to look up the molar mass of barium selenate and just apply it to the information that's given. So as you can see here, from the problem we have the grams per 100 milliliters, 280.3 grams per mole is the molar mass. And we set this up so that we can cancel out the units. And so, go to my pen. Now I'll be able to cancel out grams and milliliters. And that's my answer there. Why don't you try this one? So pause the video for a couple of minutes and try this one and come back and check the answer. All right, let's continue to see what the answer is for this one. 2.36 times 10 to the negative fifth. So you're going to find that this compound has a pretty big molar mass, something over 700. So you want to check this. This is probably the most common area for concern. Solubility product. The equilibrium constant for the dissociation of a solid salt into its aqueous ions is called the solubility product, KSP. The dissociation reaction for a silver chloride is AgCl, solid, in equilibrium with Ag positive ions and chloride ions. Notice now that's a solid and these two are in solution. So when we write the KSP, we're going to be dropping off the solid. So the solubility product constant would be the molarity of the silver ions times the molarity of the chloride ions. So if you have a formula for the compound, you can easily write the dissociation equation for it. And then balance the equation before you come up with the KSP expression. Here are a list of some of the solubility product constants. Other books have a much more extended list. Let's take a look at them now. So on the left, you're given the names of the compounds, and here are the formulas, and here are the KSP values. Notice some of these constants have really small powers of 10. Negative 38 is unbelievable. Even 10 to the negative 19th. Over here, 10 to the negative 29th. Which compound has the lowest solubility of water? Now, but this is all we have to go on. You notice it says at 25 degrees centigrade. That's important because that would affect the solubility. It's probably going to be the compound with the smallest constant. So over here we have copper 2 sulfide. And you see its value 1.27 times 10 to the negative 36. That would be the choice, followed pretty closely by lead sulfide. KSP and relative solubility. Molar solubility is related to the constant, KSP, but you cannot always compare the solubilities of the compounds by comparing these KSP values. One of the reasons is temperature. KSP values are the same whether the solvent in pure water is in pure water or an ionic solution, but the amount that dissolves would be different, and that's what we're going to see coming up. Now here's an example of a compound that's really insoluble in water, and it's used in hospitals all the time. It's called barium swallow. Now barium swallow means to actually be taking more like a slurry of barium sulfate in water. And if you're going to have this done, you probably have to drink about 1 liter of it. And you use this test to see if you have difficulty swallowing, will they see something in your esophagus, or you maybe have abdominal pain. You could have a structure there, something that's impeding the flow of food through your abdomen. Bloodstained vomit, or unexplained weight loss. How can you find the molarity of the barium sulfate that they use? Now, before we go on to the next slide, I just want to point out the barium sulfate is what is causing the esophagus here to look white. Without that, it's hard to see the esophagus when you take an x-ray. So the barium sulfate can deflect those x-rays and it can be picked up with a scan. Here's the equation for barium sulfate dissociating in water. And the constant is a very small constant. So here's our KXP expression. Remember that we don't include the solids. So I want to find the concentration or the molarity of these ions. Now they're going to be the same. So they both can be represented by X, and that's because there's one of each here. Also, I want to point out that instead of writing it this way, they just might write down barium sulfate and then AQ in parentheses, which would mean the solubility of it. So let's go back now to the math part of it. So replace both of these with x's, and that'll give us x squared. And then we're going to bring down 1.07 times 10 to the negative 10th down here, and then we're going to find the square root of that. And we get 1.05 times 10 to the negative 5th. And that equals x, which equals the concentration of both of these ions. A saturated solution of barium sulfate then has a molarity of 1.03 times 10 to the negative 5th moles per liter. Now this is a chance for you to come up with this one yourself. What's the molarity of lead chloride? KSP 1.17 times 10 to the negative 5th. And I'll help you out by giving you the equation. You notice there's a 2 here. So let's pause this screen for a second. Pause the video. See if you can finish this off yourself. Then come back and check out the solution. Okay, here is the solution. So I'm going to replace everything with x's. You notice that I have 2x here. I'm not going to include, this x here because that represents the solid when I do the math out. So KSP expression is this, but you notice the 2 here in the 2x, that 2 is now going to become, this 2 is going to become that 2 here as an exponent. Then when I replace 2x for the chloride and x for the lead, you notice that it's 2x squared. So I have to square this first before I multiply it by x. So 2x squared is 4x squared, and 4x squared times x is 4x cubed. So now I want to solve it for x. So I'm going to wind up dividing both sides by 4, and that'll give me 2.93 times 10 to the negative 6th equals x cubed. And then I take the cube root of that value. And so the cube root of that number is 0.0143. So that's the molarity of the lead chloride. Now that would be the molarity also, if we go back up here, that's the molarity of the lead, but the molarity of the chloride is 2 times that. So you got to be careful which ion they might be asking for. All right, here's another one for you to try if you weren't so successful the first time. Calculate the molar solubility of iron 2 hydroxide in pure water, and there is its KSP. So again, pause the video and try it on your own, and then come back and check out the solution. That's the answer you should get. Okay, so you might want to pause the video now. All right, here is the solution. So that's the question again. I write down my expression. Notice there's 2 hydroxides. This looks very similar to the last one we just did. KSP equals that. Same thing we're going to wind up with 4x cubed divide by 4, then take the cube root, and there's my answer. 2.30 times 10 to the negative 6 is the molarity of the ferric or iron 2 hydroxide. All right, now we're going to go the opposite direction. What if you're given the molarity or the molar solubility of a compound? Can you calculate its KSP? So here the molar solubility of silver sulfate in pure water is 0.014 molar. We always need an equation. So you have to know how to break these formulas up correctly. So you don't want to try to separate the sulfur from the oxygen now. That ion all stays together. So here's the 2 silver and 1 sulfate. So I'm going to replace the silver with 2x and the sulfate with x. So at equilibrium now, I know that these two guys are going to be in the ratio of 2 to 1. And this is the 1. So the molar solubility of the silver sulfate is 0.014, but that really means that the sulfate is 0.014 and the silver is double that. So here's my expression, and I just replace everything with their values. Do the math out, and I get 1.1 times 10 to the negative 5th, and that's the KSP. That's pretty straightforward. Here's one for you to try. The molar solubility of silver bromide in pure water is 7.3 times 10 to the negative 7th moles per liter. Calculate KSP. Maybe you want to pause this again, give it a try, then come on back and check out the solution. Okay, here's the solution. That's the question again, that's all that is. Here's my equation. My KXP expression is going to be then, get it right here. Yeah, KSP equals AG positive times BR minus, and they're the same value because it's a 1-to-1 ratio. I just have to square them, and there's my answer, 5.3 times 10 to the negative 13th. I do want to mention, if you use a table to look up the solubilities of these compounds, depending on the textbook you use, you might get slightly different answers, but they're all pretty close. Right, the effect of common ion on solubility. A slightly soluble salt dissolves less in a solution that contains one of its ions. For example, calcium fluoride will have a lower solubility in a solution that already contains fluoride ions. Here's my dissociation equation, my calcium fluoride dissociating. Notice the 1-to-2 ratio down here, 1 to 2. Now what happens when I put this compound in a solution that already has fluoride in it? The fluoride is going to inhibit the calcium fluoride from dissociating because there's already fluoride present. If there were no fluoride present in the solution, then it would go better to the right. So what do we want? We want to find now the molar solubility of calcium fluoride in a solution that already contains 0.1 moles per liter of sodium fluoride. Now remember, this molarity is both the sodium and the fluoride. The sodium ions, though, are going to be spectators and not involved in any sort of reaction. Here's our KSP from before. Now here's the difference here, in that we start off with that 1x and 2x, but I'm going to have to add on the 0.100 moles per liter from the fluoride that was already in the solution. I'm going to make the assumption that because the KSP is so small, the concentration of fluoride coming from the calcium fluoride is almost 0. So therefore, the fluoride concentration is 0.1 moles per liter. Now I write down my expression. I replace my values. So this time I have 0.1 squared times x equals the KSP, and I'm going to solve it for x by dividing by 0.1 squared. And I get 1.46 times 10 to the negative 8th. So this is a lot smaller than it would be if I had put that same amount of calcium fluoride in water. Calculate the molarity of calcium fluoride in a solution containing 0.25 moles per liter of calcium nitrate. This is similar to the question that you just had a moment ago. The difference is now we're talking about having a solution that has already some calcium ions present in it. Now why don't you pause the video and see if you can solve this one on your own. Okay, here's the equation. We have 0.250 molar for the calcium, because that's coming from here. And now we want the 2x. So we have KSP equals 0.250 times 2x squared. Remember what's going to happen when you square 2x. 2x squared becomes 4x squared. So in order to solve for x, we have to multiply 0.250 times 4, which is just going to give us 1, so we can drop that off. And then we can take the square root. So if I take the square root of this value here, that will equal x, and that's the square root of it. So that's the molarity of the calcium fluoride. The effective pH on solubility. For insoluble ionic hydroxides, the higher the pH, the lower the solubility of the ionic hydroxide. It might not seem so clear right now, but we're going to see that when we look at an equation. And the lower the pH, that means the more acidic, the higher the solubility. Well, remember, ionic hydroxides are bases, so we would expect a base to dissolve better in an acid than to dissolve in another basic solution or even water. So this should make sense. Now here's an example. So magnesium hydroxide has a very low solubility in water. What happens though if I try to dissolve this in an acid? Well, the acid will react with the hydroxide and cause a shift to the right, which means more magnesium hydroxide will dissolve. So for insoluble ionic compounds that contain anions of weak acids, the anion of a weak acid, is a base, and the lower the pH, the higher the solubility. So what happens here? I have calcium carbonate solid in equilibrium with calcium ions and carbonate ions. So the carbonate ions are again the conjugate base of the acid bicarbonate. So what happens when we have calcium carbonate in water that's becoming acidic, like the oceans? So coral reefs are made of calcium carbonate. So if you follow the equation along, if we go in this direction, the calcium carbonate produces the carbonate ions. Carbonate ions can react then with water and are in equilibrium with bicarbonate and hydroxide. So what happens if we add some hydrogen ions to this, an acid in other words? The acid will react with the hydroxide ions and cause a shift to replace them, which means the reaction goes in that direction, which means the reaction is going in this direction. So what does that mean then as the oceans become more acidic? More and more calcium carbonate will dissolve in that acidic ocean water, which means the coral reefs will start to disappear. Organisms that create shells in order to survive, they will start to disappear too because the shells are made mostly calcium carbonate. So if the oceans go, we go. All right, so let's take a look at this question here. Here you're given 3 compounds, and you're asked to determine which compound is more soluble in an acidic solution than it is in a neutral solution, like water. Well, if it's more soluble in an acidic solution, that means it should be a basic compound. And when we look at these formulas, if you recall, the anion from each formula is what could be a base. If the anion is from a weak acid, then it will be a strong base, and then it should be more soluble in an acid solution. If the anion is from a strong acid, it'll be a very weak base, and it won't be affected by the acid. So let's see what the solutions are. For A, the solubility of barium fluoride is greater in an acid solution than it is in a neutral solution, because the fluoride ion is a weak base, fluoride being the conjugate of the weak acid HF. How about for B? You might think B is the same, but let's check it out. Solubility of silver chloride is not greater in an acid. Why? Because the iodide is not a base. Because iodide is from the strong acid HI. Strong acid, weak base. Therefore, the pH will be neutral. So therefore, silver iodide would dissolve just as well in water as it would in an acid. There's really no difference. Now, the last one should be pretty easy because you notice we have hydroxide here. Anytime we have a hydroxide compound, it should be more soluble in an acid because the acid will react with the hydroxide. Yeah. So just as we expect, the solubility of calcium hydroxide is greater in an acid than it is in a neutral solution because the hydroxide is a strong base. And it's really, dissolving like this. Here's our little equation. Here we have H positive from the acid plus, well, I'm trying to write it. That's a plus. That's a plus sign. The OH, from the base is my arrow, and I'm making H2O. Okay. All right. Now, what about these two? See if you can answer that question. Which compound, FeCO3 or PbBr2, is more soluble in an acid than a base, and why? So the question is really about carbonate, CO3, and bromide, Br-. So carbonate, CO3, is from a weak acid. So carbonate is a strong base. Br- is from the strong acid HBr. So which compound is most soluble in an acid? This guy. Okay. Now, precipitation. Precipitation will occur when the concentrations of the ions exceed the solubility of the ionic compound. So prior to this, you should have done chemical reactions, probably in Chem 1, where you would be given two solutions that are soluble, two solutions, and you would add the two solutions together. And a precipitate would immediately occur or form if the concentrations of the ions that are forming that precipitate, which is an insoluble compound, are a certain amount. But the ones that you would have seen in Chem 1, the concentrations are all pretty high because they wouldn't have brought in this idea of KSP with it. So we're kind of building on what you had in Chem 1 in terms of precipitation. If we compare the reaction quotient Q, which we saw when we studied equilibrium, for the current solution concentrations to the value of KSP, we can determine if precipitation will occur. If Q equals KSP, the solution is saturated and no precipitation will occur. But if Q is less than KSP, the solution is unsaturated, no precipitation will occur. Finally, if Q is greater than KSP, the solution will be above saturation, which means supersaturated, and the salt above will precipitate out. So you will get a precipitate if Q is greater than KSP. That's what you're looking for. For it to be saturated is pretty tough. It's hard to have just the right amounts of these things so they're equal to each other. It's probably going to be one of these two. Some solutions with Q greater than KSP will not precipitate unless disturbed, and these are called supersaturated solutions, and we'll take a look at a picture of those. All right, so let's take a look at this one first on the left. We have sodium carbonate, Na2CO3, and the sodium carbonate is in solution. It's this yellow solution. Sorry, not carbonate, but sodium chromate. Chromum actually means colors. Now down here in the water, you can't see it, but what's dissolved is silver nitrate. So once the drops of sodium chromate hit the solution containing silver nitrate, a chemical reaction occurs. The silver combines with the chromate, and you get this kind of a reddish-brown compound. That's our precipitate. So Q must be greater than KSP. Now what about for supersaturated solutions? Now you don't see a lot of these around because they're very unstable, but one that can be made easily is sodium acetate. How do you make a supersaturated solution? You determine how much you would need to make a hot saturated solution. You make that and then let the temperature drop. And as the temperature drops, instead of some solid sodium acetate precipitating out, it stays dissolved. And so you wind up having more sodium acetate dissolved than should be at the lower temperature. But it's very unstable. If you stir that solution, shake it up, even just move it from one place to another, you can wind up having the precipitation happen. And that's what's going on here in the two pictures. They put a seed crystal, which is a crystal of sodium acetate. And once it hits that solution, that causes much, much more precipitate to happen. And what happens is dissolved sodium acetate clumps onto the seed crystal that was added to it, and it just mushrooms. And you could just, heat this up again and come back. If you heated this, not to the boiling point, but you heat it enough, this stuff will all redissolve when you wind up with a supersaturated solution. And when this happens, a lot of heat's released. So this stuff actually is what is in a heat pack that you can reuse. It's supersaturated sodium acetate. Okay. Predicting precipitation reactions by comparing Q and KSP. So in this example, a 0.15 molar lead-2 nitrate solution is mixed with a 0.00350 molar sodium bromide solution. Does a precipitate form in the newly mixed solution? First, we determine the possible cross products and the KSP values. And what the cross product means is that the positive lead ions from the lead nitrate may combine with the negative bromide ions from sodium bromide, or the sodium ions from sodium bromide might combine with the nitrate ions from lead nitrate. So we could look them up to see if one of those products is soluble or not. And then what we find here are two possible products. Sodium nitrate, always soluble in water, but lead bromide, KSP, 4.67 times 10 to the negative 6. So this would be our precipitate, if it forms. Now, to know if it forms or not, we got to calculate what Q is and compare it to KSP. So to calculate Q, we have to know the molarities of the lead and the bromide. So here is the expression. All we're doing is putting in Q instead of KSP. And then we plug in the molarities for these ions. So remember, the lead ion was 0.150, 0.0150. It's right here. That's the lead ion concentration. And the bromide was from the other solution. So all we have to do then is square the bromide and then multiply it by the lead. And we do that, we get 1.84 times 10 to the negative 7. Now we're going to compare that. We compare this value with the KSP. And this is smaller than KSP, therefore no precipitate will form. Why don't you try this one now? If the original solutions are concentrated through evaporation and mixed again to form a solution that is 0.0600 molar in lead nitrate and 0.0158 molar in sodium bromide, will a precipitate form in the newly mixed solution? So pause the video and answer this one, and then come on back and see the solution. Okay, here we go. I'm going to write down Q equals the lead times the bromide. And now I have my new concentration to put in. I get that for a value. And in this case, Q is greater than KSP, so a precipitate will form. Hope you got it right. Okay, precipitating cations selectively. Our example, magnesium and calcium ions can be separated by adding hydroxide ions. The compound with the lower KSP will precipitate out first. So here are the two compounds, and here are the two KSPs. And we can see by far, magnesium hydroxide has that lower KSP. So that's the one to precipitate first. So we're going to add sodium hydroxide to cause the magnesium hydroxide to precipitate out. So here's my example up here. Now this is talking about seawater. So here's the magnesium ion concentration. Put the line over that. And here's the calcium ion concentration here. So here in this example, they're adding potassium hydroxide, which will give us the hydroxide that we need. They want to know what's the minimum amount of hydroxide that will cause the precipitation of the magnesium. So the precipitation commences when the value of Q for the precipitating compound, which would be magnesium hydroxide, just equals the value of KSP. So we're going to set the expression for Q for magnesium hydroxide equal to KSP for the hydroxide. This is the concentration which will precipitate out, and it looks like this. So Q equals the magnesium times the hydroxide squared. We know the magnesium is up here, 0.059 molar, so we're going to solve it for the hydroxide. So we start off with Q being the same as KSP, which is over here. So all I do is kind of flip this around. So now this thing is on the left and the KSP is on the right. So we want to solve it for hydroxide. So I'm going to isolate the hydroxide, but I'm going to divide by 0.059. So I would do the math here, take this value, divide it by that, make sure you say equals, and then I take the square root. And that's what I get for an answer, 1.9 times 10 to the negative sixth. So that's the minimum concentration that'll cause precipitation. For practice, let's plug in a different value for the magnesium. So instead of 0.059, we'll plug in 0.025 and see how the minimum then will change. Now you notice 0.025 is less than 0.059, a little more than half that. So let's do that one out and see what we get for an answer. Again, solving it for the hydroxide, we get 2.9 times 10 to the negative sixth, and that's pretty much a little bit like half of the other one. Okay. That's the end of the show.